And so you have multiple different types. You can have a shift by 0, a shift by 1, a shift by 2, or a shift by 3, based on the inputs from the shifter that are 0, 0, 0, 1, 1, 1, 0, and 1, 1. Yeah. But we'll kind of get to that. Right. So depending on which input you get, the 1, 0 just stands for that it's going to be 2 bits. So like this row right here, the most significant bit would be SHAMT, or the shift amount 1, and this is going to be shift amount 2. Yeah, exactly. So you just like, this defines how many bits you're going to shift by. And so it can go up to 4 or to 3 because of these different options where it's 0, 1, 2, or 3. And so you can shift your A by that many moves or bits or whatever. So if we have a shift amount of 0, right? And then we look over here and we look for each individual mux, where each mux is one of the letters, right? And so we see, okay, if it's 0, 0, which is the first case where it's 0, I don't know. She's probably going to give us a table or something maybe to fill in. Because I don't feel like she's going to make us design the entire thing. I feel like that'd be like a really long question, and we didn't go over it that much for this. But I mean, I don't know. But so let's just talk about each case.
It's possible that she'll give us the muxes already, and we just have to draw the lines in.
That could also be true. Yeah. I mean, she could give us whatever. But then again, I feel like because she doesn't make the quizzes, the TAs do. So, and none of the problems on the homework. I mean, there could be one for sure, but I don't know. They didn't even give us any like homework book problems this time. So there's just a lot of stuff that's like weird, but whatever. We're just going through each one, right? So if A3 and Y3 are just the most significant bits, whether it's the input or the output, if the shift amount is 0, then A3 is going to stay where it is. If it's 0, A2 is going to stay where it is. If it's 0, A1 is going to stay where it is. And if it's 0, A0 is going to stay where it is. And that kind of makes sense. Because if you shift by 0, it's going to be the same output, right? So if you gave it 1, 1, 1, 1, it's still going to be 1, 1, 1, 1. So in the case that it's 0, 1, so you shift by 1, right? In that case, it's going to be 0. For the most significant bit's going to be 0 because it goes from 1, 1, 1, 1 to 0, 1, 1, 1, right? And then if you shift by 1, A3 is still there. A3, which was the most significant bit, is now the second most significant bit. And it just kind of goes down the chain, right? So each one gets shifted by 1 bit here. So A2 was 0, 0 here, and now it's 0, 1 here. And A1 was 0, 0 here, and now it's 0, 1 here. It's just kind of, if you shift by 1 or by 0, then the most significant bit doesn't change, right? If you shift by 1, 2, or 3, the most significant bit becomes 0. If you shift by 2, the most significant bit is 0 as defined up here. And then the second most significant bit is also going to be 0 as defined by here, because this is 1, 0, right? 1, 0. And then the third most significant bit, because we only shifted by 2, is going to end up being A2. And then, or A3, I'm sorry. And then the last one is going to be A2. And the top one was 1, 1, shift 3. What do you mean? The top one is shift 3. The bottom one is going to be shift 3. because the binary 1, 1 is 3. So the top one is this one is like no shift. Yeah, I can remove the writing. Okay. Okay, no. That's right. Okay, I'll explain that. So think of this. Let me write some more stuff here. Right? Okay. So let's look over here. These are correlated to this value, the shift amount, right? And so this is going to be the input for shift amount. Yeah, that's why Onion explained it. So in the case that you shift by 0, the most significant bit of the output, which is Y3, is going to stay the same as it was originally. So if you select 0, 0, it follows the path and it picks A3, which it's supposed to. If for the second most significant bit, again, follows the path, chooses 0, 0 like it's supposed to, and takes the second most significant bit because there was no change. In any case where there's a shift amount, yeah, the output is Y3, Y2, 1, 1, 1, 0. Yeah, I guess I could explain that better for sure. And then the only other thing to notice is that, like, in this case, it's very similar to how the last quiz was with that, like, upside down triangle. The upside down triangle is just specifying that the value is going to be 0. In the case, like, the value will be 0. I'll go shift left. Yeah, it would be this. It would be the same but switched. The triangle going out is just saying that all these values that it connects are going to be 0. So, for example, this 1, 1, if there was a shift by 3, Y1 is going to be 0. And if there was a shift by 2 or 3, the Y2 is going to be 0. And if there's a shift by 1, then Y3, Y by 1, 2, or 3, Y3 is going to just the triangle represents like false ground, whatever you want to call it. If you're like in circuits, it's ground. If you're designing circuits and stuff like that. Yeah. Okay. S1, yeah, that's from the shift amount. And it's just like your selector of the 1 and 0 just say that you're gonna one's gonna be S1, one's gonna be defined as like S1, which is the most significant, and the other is gonna be defined as S0, which is the least significant. Y0 doesn't mean shift anything. If you have a like let's say where is this? So let's say you have like a binary number that's just like 4 ones, right? This is A0. Oh, that's gonna be really shitty. Or no, that's not A0, sorry. That's A, yeah, like this is gonna be A3. This is gonna be A2, this is gonna be A1, and this is gonna be A0, and it's the same case for the output. So the least significant bit is gonna be Y0. This bit is gonna be Y1, this bit is gonna be Y2, and this bit is gonna be Y3. It's just like this number correlates to which bit it picks, if that makes sense.
It's the furthest left bit. Y3 is the furthest left bit.
Because it's a 4-bit, right?
No,
And so,
I mean not like Y. I'm saying Y3 is the leftmost bit. It
oh yeah, yeah,
corresponds to
yeah,
the leftmost bit, not the furthest right.
yeah, 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 exactly. In this case, and that's why like when you see stuff drawn out like this with a 3 to 0, this is just saying that you're gonna have a A3, an A2, an A1, and an A0. And so like if like this was 2, then it would only be like 1 to 0 as it is here, because you're only gonna have like a 1, a shift amount 1, and a shift amount 0. There's only gonna be 2 bits in that case. Exactly, yeah. Y3 is the most significant bit for the output because these are all these are all the output right here. So yeah, shift design, I mean it's not terrible. It's just there's a lot to it. So if she gives um a problem, hopefully she has it pretty laid out already. Cool. So now register files. Yeah, sure. Yeah, definitely like a fill in the blank type of thing if she even asks it, but who knows if it's even gonna get asked. Um, so we'll see. Like you might fill in which ones are 0 or which ones are A3 or A2 or A1, like how she had it with the with this, where we say like this is A3 when you shift by 0 and that sort of stuff. It's just like so like in the case, let's talk about it like this real quick and then we'll go on to the other stuff. Um, if we shift by 0, right, and we're given A, which is a 4-bit, and we want Y, which is a 4-bit, like if we shift by 0, Y is going to be equal to A, right? Because we're not shifting, we're not changing anything. If we shift by 1, the most significant bit, because we shift in this case to the right, is going to be 0. And then everything else is just going to follow what like got shifted. So A3 is now Y2, and A2 is now Y1, and A1 is now Y0. It's just like because you shifted over by 1, you just shifted over by 1. I don't. I mean, yeah. And then if you shift by 2, right? Like the first, because you're gonna have 2 zeros in the front. So you shift by 2, so you had a 0 here, a 0 here, and then now Y1 is A3 and Y0 is A2. And it's just plugging them in. That's gonna be like the best way to do it. I mean, if she really gives us something like this, you can just kind of memorize it and try and write it out. But it's like Y2 is the Y2. So like if you have an input, right, and we're gonna say that it's a, can we do subscript? All right, I don't know how to do subscript. So let's just say like this is A and we'll say 0 and then, or this is actually A3. A2, A1, A0, right? And this is if that's your input, then your output is going to be Y3, Y2, Y1, and then Y0, right? And so then if you shift, right, let's just like write a bunch of these out. So let's say this is your input, and then you shift here by 0, right? If you shift by 0, they're going to equal the same thing. So this is going to equal this. This entire like output is going to equal the input if you shift by 0. If you shift by 1, your output's going to become 0, and then it's going to be A3, and then it's going to be A2, and then it's going to be A1, right? Because you shift by 1, so it becomes a 0 in the front. And so if you shift by 2, then it becomes 0, 0, A3, A2, and then you lose the other 2 bits. And if you shift by 3 and so on, right? So it's like it's 0, 0, 0, and then A3, right? And then if you shift by 4, then you get all zeros. And but we can't because we only have an ability to shift um, by 0, 1, 2, or 3 because we only have 4 bits.
Well, we potentially shift more, but our mux only has 2 bits, so the max we can
Correct.
shift is
Yeah.
3.
Yeah. In this case, it is, and I don't think she'll give us a case where we shift more because that's just pretty much pointless. But just think of like this as written out like this when you actually write out the answer. If you did shift 4, then Y0 would be 0. The design won't change, no. But we can't shift 4 in this case because we can only shift by, because we have 2 bits, we can only shift by either 0, 1, 2, or 3. It depends on how many you shift, right? It can be any of the values depending on how many you shift. Well, I mean, we can talk about it a little bit later too, but let's just go on to register files because that's like more of the important stuff for this actual like quiz. So, will the time delay for look ahead adders be on the quiz? I don't think so. I believe it's only going to be like the ripple carry, and it'll be questions like the homework where it's kind of like you have a 4-bit adder, add them together. Cool. Register files. In like a rough example, this is like the internals of the register file. So like if we look here, right, you have in this case like a 4 by 16 bit. So we're saying that each register is 16 bits. We have 4 registers, right? And we want to do an operation because that's like what register files pretty much do. So in a register file, you give 2 operations to an ALU, and then it comes back and it gives you an input. Depending on like where you want to write, if you want to even write with your write enable, excuse me, and then you have your 2 reading inputs up here and out here. So we can kind of like start from the basics real quick. I don't think the slide's super useful. So you have an input, right? It's similar to last quiz, so we're not going to go over it like too much, unless we want to. But you have 4 registers. Okay, in this case, you have a load, you have a clock, so it's like the register is the same. So I'm not going to talk too much about that. But in this case, you have an input. Each register has its input, right? And then depending on which register you're selecting to do an operation, like a simple operation like A plus B, or C plus D, it's just like that's how it chooses. You have to actually download it and open it. And if you're on a Mac, you can use numbers. It still shows up. What's I? I is just the input. We don't like necessarily know what the input is in this case, but I is the input, and so it's like the data, right? So registers are given data if we want to write to them, and in this case, that's what I is. So it's pretty much like you choose one of the 4 registers with this mux, and you choose one of the 4 registers with this mux, and then you give your selector to the ALU like we were talking about earlier, and it does an operation with the 2 based on what you chose. So it's not super complex. Um, And so I see it if we left the first. Most significant bits to use the selectors for the individual directed. Yeah, that's similar to the homework problems. Because they want us to like this won't she won't ask us to draw one of these out because I don't even she likes drawing them out like according to how this looks and how she was in class. I think she's gonna ask more questions that were like on the homework and stuff that looks like this, where you have a register file and then you need to expand it, like how it says in the homework. So we'll talk about that more. So we're only gonna go over this for like a couple minutes. But pretty much register files are used to take multiple registers, do operations, and then write back to those operations or write back to those registers, right? And so if you have your write address and that register you're gonna you have your write enable, which allows it to actually write. It's kind of like a load or something like that. And then you have your muxes, which choose your two registers to do an operation on. You have selectors, which choose what type of operation to do inside the ALU. And then that ALU output goes back into the register file as the input. So when all in all, a register, if you look at it, it looks like this. You have your data input, your write enable, your write address, and then like this would be going into your ALU. So in the end, it looks like this is like a better example. You have a read address, a write address, which chooses the two register files inside. You have two read addresses, which chooses what register files to read from. You have a write address, which chooses where to write if it is enabled. And then you have a data input, which comes from your ALU. Yeah, all the register file notes are handwritten. Yeah, they are. But again, like if you understand the homework, which we'll get to very shortly, it's not that bad. Like it's really not that bad. It's just like a register file. You need a way, okay, right? So like if you have a bunch of things in a register file, you have to think of it as like super simple operations. I don't know. We can look real quick. It's not in the book, according to this. If you can find it, good luck. But she didn't give page numbers for it. So okay, real quick, register file, right? You have to think like a register file just has a bunch. Oh, there you go. Section 5.5.5. A register file has a bunch of registers inside of it. It's literally just like controlling a bunch of registers. And so you have to do a simple operation, which takes two registers and does an operation. And that's what the first address does and the second address does. It chooses which two registers to actually do an operation on. Okay. The write address is just where you want it to be. So if you said A equals B plus C, then you're going to say your write address is going to be whatever address to register A. Your read address is going to be to C, and then this is going to be to B. I can repost them in Discord and real quick. Let's see. Downloads. Oh shit, it's too big. Let me see how big they are real quick. Oh, cool. There you go. Holofires has it. So anyway, so those two read addresses go and are choose your registers, and that goes into your ALU. Your ALU then computes something, and then gives your data input back into the register, which data exactly. Just yeah, I mean, like it's weird to think about, but yeah, it's not that complex. These two select what you're reading from, what the R values are going to be in terms of like C++ or something. This is your L value. It's like your variable that you're saving inside. Your ALU actually does the operation and it comes back and stores it inside of there. Let's see what else. And the output goes into the right address. No, it goes into the data input. There's assembly quiz too, Sneaky. It's online now. But it's there's assembly on the quiz. It's online. But we'll do that later as well. Okay. Let's go on to the next thing real quick because she's not going to ask us any questions, so we're not really going to go over the phrase of like how she talked about it in class, like this. This isn't going to be on the quiz, for example. Yeah, slide 54. We can look down there. I can look there real quick. All right, so there's going to be ALU design like we talked about, adding and subtracting. So like with full adders and ripple carry adders, we're going to have shifters, register files, which is kind of what we're going over real quick, and then we're going to have the SRAM, DRAM, and the ROM, which we really didn't even go over that much, but it's to the extent that it is on the homework. So, for example, like I don't really feel like we should talk about the other stuff in here because she didn't really talk about it well. I don't know. I mean, we can go over it real quick. The hardest part of the quiz, honestly, probably just making sure you choose the right operations for adders and stuff. Like the register files are like going to be pretty simple. They're going to be similar to like what last week's quiz. Yeah, not yeah. Let me pull up last week's quiz real quick because that's kind of what it's going to be ish like. In terms of this problem, so like this right here is practically like half of a register file. Yeah, the answers to the last quiz are online on the website. There's a section for quizzes. This is literally like part of a register file, right? Because you have multiple registers and you have like your decoder, which chooses which register. And so like this selector would be your address, which chooses which one you're going to, that sort of stuff. A register file is literally just a bunch of registers together. That's literally all it is. So a register file, yeah, exactly. It's not that complex. So technically, like this was a very simplified and incomplete register file for the last quiz. And so that's pretty much what this next quiz is going to be like, right? Because if we look at this problem, all it is just choosing more freaking registers. I'm gonna go through more of it tomorrow too, but probably until like 7:30. I feel like that's like when we're gonna end up kind of being done. So yeah, so I don't know what else to really like say for that. It's just yeah, we're gonna go on the homework stuff real quick. Yeah, it's hard with the design and stuff because it's just like it's super different. And then you start looking random stuff up. It's like it's different depending on what like example you're looking. So yeah, I feel like we can just kind of like go over the homework and stuff because again, like the DRAM, SRAM, and ROM, we didn't really go through enough to actually have like homework questions as like to the extent that she does. Um, yeah, I feel like I don't know. That's my personal opinion. Um, I don't really think there's that much to it. Um, so the only thing to realize is that ROM is read only. That's like pretty much it. And so if she asked a question, maybe like which one could you read or write to, or she gave a question where she like drew. I haven't found any. If anyone has, definitely post them. But for example, like really quick, this question, because we have read or write, this is a register file, but like in this case, it says read only memory, right? And so we have a chip select. That's what that CS value is because we can't read or write to it. So she might ask a question like as like a part B or part C or part D or whatever, and like what type of memory can you only read from? And that would be ROM. But yeah, there's not that much to it. Let's just go over the homework questions real quick. That's pretty like important. So this is designing the ALU, right? And so this is probably something that what it might be. Yeah, okay, go for it. And yeah, I'm sorry that it's like super scrambled and stuff because like I'm trying to remember half the shit as I like explain it. But so in this case for question one, does everyone kind of get what's going on here? Are we chilling? Like you have this is like a sort of question that we'll get, right? So it's design an ALU. Are we chilling? Design an ALU for these four operations, right? And so they gave us this for the quiz, and we just have to like draw out this section, right? And so we have our A or B output, and we have our C in output. And so we look here, we have A plus B plus C in, A and B, A or B, or just A. C in is the carryover, is the carry input. And it's used more in carry ripple adders, which is what we're kind of like talking about here. But when you're adding a bunch of bits individually, right? Because if you have 1 plus 1, you're gonna have 0 as your output, but there's a carry over of 1. And so that carry over goes as the C out into the next C in. For example, if we look at this question, right? We have C in here and it goes through all of them because when you add two numbers, if it's 1 plus 1, right? This is like back to the first week when we were talking about, yeah, this carry out becomes the carry in pretty much. Okay, let's go back to the first question real quick. Let's see. All right, am I on share for a second? Okay. Maybe 5 week up. Damn, honestly, I have to go work on my 45C project tomorrow, during the day, which sucks. I don't want to do that. I don't think it's that bad, but I haven't really done that much for it. I mean, shit, we have a while because it's not due until next Monday, so I'm not like stressing about it. I'm gonna try and get it done this week though. Hopefully even tomorrow. It's cancer. Oh, that's another thing. Did you guys see? I don't know, for any of the people taking 45C, they switched the professor for the earlier 46 lecture in the fall. So it was the 4 o'clock one because there's a 3 o'clock and a 4 o'clock. The 3 o'clock was supposed to be staff, and it was supposed to be Gago, and then they switched it so now the 3 o'clock is Pattis instead. So I don't know if you guys like worked out your schedules and stuff, but the 3 o'clock is Pattis and the 4 o'clock is Gago as of now. So that was kind of crazy to see because I wasn't expecting them to switch it, but I'm happy about that because I can only take the 3 o'clock one next quarter.
Yeah, because I took Gago for 6N last quarter, and like I went into his office hours once, which he only has like 1 or 2 hours a week, which was just stupid for 3 or 4 classes that he was teaching. And like the line out the door was like insane for 46, and I was like, I just wanted to ask a question about fucking linear algebra, but like it took probably like 40 minutes. Oh shit! Did you take 6N last quarter too? Oh shit! Yeah, that was definitely weird. Um, I got like really really lucky. I was A-, and then the extra credit brought me like right above. So I got an A, and that was so chilling. But um, yeah, we're talking about fall enrollment. Damn, last year here with the 20th. That's impressive. I wish I had the 20th. Yeah, if you have to go with the 4 o'clock, it's probably going to be Gago. One second. Okay. Let's see. Okay, whatever. Fuck it. I ended up doing above average. That's all that matters to me. I got like I don't remember. I was in lecture A, so I was at a 38. I think it was in like an 82 or an 82%, 81%, something like that. Yeah, we're gonna go over that for this question real quick. Okay, cool. All right. So question 1. This is the LLU design. It's just so you have a selector S1, S0. Okay. The selector chooses one of these. You just kind of like work it backwards, right? So in the case that it's be A, right? So you can just go back and grab A. You don't have to do anything with it. In the case, that 1, 0, then it's an OR as defined up here, and so you just follow back of A and B. So you just make the inputs A and B, and I mean like it's confusing because it's so small, but you just kind of have to get used to it, I guess.
And then 0, 1, and B, right? And so then that's just an AND of A and B here. Do jump. No, she doesn't do the jump. She makes, but I mean, honestly, the jump here would like make it look really fucking. She just uses the dot to show that like it's a branch. And then for it's the adder, and it takes the C in, the A and the B, and it adds them and gives it like it's a relative ALU here. The jump is like if you have a line going down and you jump over a line, it's like a little hump. That's what the idea of like the jump is. Yeah, it looks really confusing, but I mean, yeah, it kind of is what it is. So yeah, and then the C out, because you have to remember that the full adder has a C out in this case, but we just ignore it because it doesn't really matter. So you can just kind of draw it out and forget about it. Let's look at the next one. Is a little more complex. So for this one, the first one again is A plus B plus the C input. So again, the same thing here. This one, A and B, again, the same thing, just A and B. And then for 1, 0, this is A and B in parentheses or C input. So we take the C input and we OR it with the AND of the A and B, right? And so it does these two, it brings them together, and then it gives us our input, or output, sorry. And then again, A is just 1, 1, so you just branch out of A and you give it to 1, 1. When there's adding, you use an adder, yeah. 100% of the time, you're always going to use an adder, and you will get like a C in value. Just remember that the C in always goes into the adder. And then again, you have to have a C out that in this case does nothing, but there's at least a C out. C in, it's for carries, right? So like if 1 plus 1 in binary, right? 1 plus 1 in binary, if like you're going across and doing binary as we did in the first week, is equal to, if you're adding two, it's equal to like 1 with a remainder, with a carryover of 1. Or 0 with a carryover of 1. Yeah, the carryover is going to be 1 and the value is going to be 0. That would be the C out, which would turn into the C in for the next bit. Exactly. When there's a C out, but it doesn't tell us to do anything with it, then you just completely ignore it. And the only time we're really going to do anything with it is in the case of something like this, where it's a chain, a ripple chain. And that's the only time it's going to be used. So pretty much anytime that you see it's just a simple addition or something, you can just kind of do it. But make sure you draw it because it's probably something that'll take points off. If it's 1 plus 1, the C out, it's going to be 1. Wait, no, it wouldn't be 1? Yeah. C out will be 1, but the value is cool. Great. Does everyone kind of like get this C out too? It does, kind of. It takes, right? So remember like the first lecture, we're going to get to that, Harmon, because like the next question talks about that. Yeah, it kind of, it's like, remember when we were talking in like the first quiz and stuff, when you had to add two binary numbers together, and when you add like 1 plus 1, it makes it a 0 and then carry over 1. That's the carry out. That 1 is the carry out. And so the adder is of those two, the carry out gets sent out into the next one, right? And so then let's say that you have 1 and over 1, and so it's like 1 plus 1 is like the 0 with a carry out of 1. And then let's say the 1 to the left of that, if you were adding those two, is also 1 and 1. because you had that carry in or the carry out of the one before, it makes it 1, but also with a carry out of 1 again. It's just kind of like it's a really long chain. It's similar to this problem here, right? Because it's just the carry out or the carry in goes in here, but then it's a carry out which goes into another carry in. It's just like a really long thing, not necessarily a loop because it's not the same one, but it just changes back and forth until it's finally a carry out, and we don't need it anymore. These are XOR, yeah, and I'm going to explain why they're super helpful. I mean, you could do this, and it's really simple, but it just like if you were to go any further, then it makes more sense to draw it like this. What's problem 2? Problem 2 is just in the ALU design. Is everyone good on the 2 ALU problems quick? Cool. They're not like super complex here. It's literally the same thing practically. The only difference is in this case you have A and B or CN. And then this one is A. Yeah, and we can go over it more tomorrow and stuff as well and just kind of like review it. But I was about to say, Halifax, like, are you just trying to brag out here? Or fucking 20 seconds. Is reducing a 3-bit ALU to a 2-bit one. I don't feel like we're gonna have to do that with ALU, right? I think we'll have to do it with the memory files and stuff like that, if I'm not mistaken. Because the ALU is not going to change. Like this won't change, even if it's a higher like bit. Oh wait, you mean like taking multiple things and then like if it was like 8 operations and turning it into a 4 out. I think that's what you mean. Okay, yeah. Yeah, that's gonna be like the biggest, like the trippiest thing probably. No, you're good. It just took me a minute. That will definitely be like the hardest thing, but I think I have a problem that we can do maybe today, maybe tomorrow. That like this stuff, and that'll like kind of like simplify it out real quick. Cool. So okay, so question 3. Yeah, exactly. That's what the XORs do for this question. So pretty much you have, and this is like just like specifying, right? So this says like A3 to 0. If you were doing like A3:0, that's just specifying that there's an A3, an A2, an A1, and an A0. And so in this case, right, if we draw it out, our C input's going to be 1 because it is a subtractor. So because it's a subtractor, our C input's going to be 1. What's B and A? I mean, like, it doesn't really matter what they are per se. They're just 2 registers with a value that is 4 bits. So like it doesn't like necessarily matter. We just know they're 4 bits, and that's why you have A3 through A0 and B3 through B0. And so you have to add them up with each bit individually, right? Because like you don't want to add the most significant bit of B with the least significant bit of A. So you just like that's why you keep the 2 zeros together. And so in this case, right, we want it to be a subtractor. And so XOR gates, remember, are when it's when both are not the same that it's 1, I believe. Is that right? Okay, cool. So you have a C in, which is 1, again, because it's subtractor. So we go through here, right? And so B0, if this least significant bit is 0, and then the C in is 1, and that makes it 1 because we want the opposite, right? So then we do A, because we're saying A plus the inverse of B plus 1. So that's pretty much what this is doing right here. And then it's just going through and doing each one. You could write it out and just use the inverse if you want, because we know it's only a subtractor. You could just do the inverse and say screw it. You can in this case. It's just like if you were to like continue register design or computer architecture and stuff like that, you're probably not going to see this. You're just going to do this. So yeah, the simple way is just to say you have an input, which is 1 because it's a subtractor, and then you're giving it A and the inverse of B. That's like the simplest way to put it. So if you wanted to just do this, this also apparently gets credit. So if it says make a 4-bit subtractor, then you just take the 4-bit subtractor, you put a bunch of small 1-bit full adders, you do a carry over with the C, and yeah, you just turn B into the inverse. And so you're saying A plus the inverse of B, and that's your answer. Is everyone kind of cool with that for now? Well, okay, so in this case, it says for form A minus B, so B is going to be the inverse. Yeah, so inverting a 2 complement number is doing that and then adding 1, but that's why our CN is there. And subtractor is definitely going to be on the quiz. That's like practically a given. She wants that. She likes that. Okay, so if we have 2 binary numbers, let's just say like 1 and 1, right? That's too much. So if we wanted to subtract these two, and let's say that this is A and this is B right here. If that's B, then we're gonna do the inverse of this. And so the inverse of 0 is gonna be, so I'll just write the inverse out real quick, right? And so this is the inverse. So then you just end up adding these two and adding a 1 at the beginning, right? And so if you were to go through, then you just kind of like that's pretty much how you do it. Or adding a 1 here, right? So then that turns into what, 1 0 1 1 or 1 0 like this, and then you add these two, and that should be your answer. So like if you have, when we're, and correct me if I'm wrong because this is a while ago, so I don't know off the top of my head. So if you have A, which is this, and you have B, which is, let's say this, right? And you want to subtract B from A, you have to flip it and then add 1, right? So you flip it and then you add 1. So you add 1 here, and then that's how you get 1 0, right? And so then in the end, you're left with 1 1 1 1, and then this. Yeah. And so then from there, you just add these two together, and that would be your answer. And yes, and it still can overflow, and that's what your C out is. It's your carry out if it overflows. The answer, I think, would be what it would be 1 0 0 1 1. Saying that like this is specifying that it's negative, and then this would be your answer, if I'm not mistaken. Unless somebody wants to tell me I'm wrong, then yeah. Because you still have to add, once you solve for this, you still have to add these two together. Like you still have to do the actual addition for that. And then once you add them together, you would get like, theoretically, this is your output. Yeah, exactly. Cool. Okay, are you guys good coming on to the next problem? We're going to the next problem. Okay, cool. So this is another ALU. This is the case where we actually have to use, and this is why it's convenient to use XOR. So I'll get there in a second. But right, so we'll come up here. So pretty much the question says making a 4-bit adder subtractor using 4 1-bit full adders. Maybe mux is another logic gates to determine the value sum in the following table. So when S, which as we see here is going to be our C in, right? Because we know that you have a C in and then you have 2 other inputs into a full adder, right? And then you also have a C out and its actual value. Does everyone get that? So you have an input for the carry in, you have an output for the carry out. You have your 2 inputs for the registers, the A and the B, and then you have your actual value output for each individual full bit adder. So this S defined here, it becomes our selector between adding or subtracting. And in this case, it can also be considered our carry in. Because if we add, like it shows here, we want the carry in to be 0. And if we subtract, we want the carry in to be 1. Kinda, yeah. It's like the selector again. But you have to remember that like in a full bit adder, right? If we subtract, we want the C in to be 1. Yeah, subtraction is always going to have the C in as 1. So if we want to go down and let's click, you have 2 options, right? You can give it your S, and then you can go and put that S into a mux, choosing either if you want to have an invert or you want to have the not invert if you're adding, right? Because we know that the selector, if it's 0, it's adding, and if it's 1, it's subtracting. So we can do that up here, right? Or, which is really nice, we can just use the selector as part of XOR gates. And so if the selector is 1 and the value is 1, then it'll be 0. It's doing the inverse, but making it a lot easier instead of, having a bunch of muxes and stuff in here. So if you wanted to go through this, you're saying that if the selector is 1, doing a subtraction problem, right? Which means that Cn also needs to be 1. And then if we go over here, the rest of this is literally a copy from the problem above. So if we go here, right, the selector is 1, and then let's say that B0 is 1, that makes this 0. So you're doing whatever A0 is plus 0. And then let's say that this one was 0 and this was 1, then it's going to be 1. So you're doing A1 plus 1. And so it's just going down the chain. But you know that when you use subtraction, you want to do the inverse. As long as the carry in is already given for a subtraction problem, you just want the inverse. And so we know that if it's already going to be a 1, if it's the same, then it's going to be 0. And if it's the opposite, it's going to be 1, which means that it's doing the equivalent of just putting an inverse there. Is there any questions with that? I mean, like it's like a lot to understand from just like hearing words and stuff, but like ask questions and hopefully like that makes it clear. Yeah, exactly. It acts as the negative B or the not B. The tilde is considered the not, so like the inverse. Cool. So everyone kind of like understands the question, kind of maybe. When Cn is 0, it's an addition. Yeah. Those 3 and 4. Like you mean for the actual questions. So because this is a subtractor problem, where did I pass it? Because this is a subtractor problem, we always know Cn is going to be 1, right? And that's why we can do it like this. And we can drag that down and apply it here because Cn can be either 0. And if Cn is 0, we know it's an addition problem, or for most of it, we know it's an addition problem pretty much. And so in that case, it allows this to work, because if it's 0, then we're not doing the inverse and adding. So if you give this 0 and this is also 0, then it turns 1. You can add them together. It's just because the selector is different. Because when the selector is 1, then you know you're doing subtracting. If it's 0, you're doing addition. So it allows you to do it properly. If this makes more sense to you, like using the muxes and everything like that, the mux to determine whether it's like 0, 1 for adding or subtracting. Yeah, exactly. The selector isn't defaulted. It can be either or. It can be either or, like an add or a subtract. So if the mux makes more sense, though, I mean, it's totally up to you. Let me post a couple of pictures just for people for the adder part. I mean, if mux makes you understand it better, then use it, because I mean, when it comes down to it, it's just like what works better, what do you understand better. I'm gonna post it in the resources one. And that's for subtracting, and this will be for adding maybe. Let's get, cool. Okay. Yeah, see you later. Okay. So yeah, so let's go back over there. So I mean, if the muxes make more sense, use the muxes. The XOR is like it's weird to think about if you don't like understand it. So use the muxes. It's literally in that case just putting that selector into the mux and making it 1 as like defined up here for it to be negative, or making it 0 otherwise. So yeah, so just use the mux. Like if the mux works for you, then yeah. I just don't want to write more in the test, so I'm gonna kind of like memorize this and then just write this out, because yeah, I don't want to write out the mux and everything like that. Yeah, honestly. But yeah, whoever was gonna post it, I think it was Harmon. But yeah, post it if. Oh, no, not you. I don't know. Whoever was gonna post it, whoever was recording it, I know someone was. Yeah, you're right. Yeah, Paprika said he, or she was gonna post it. Okay, cool. Lit. Yeah. So okay, is everyone kind of good with this problem then? Because it's just like use the mux if it makes you feel more comfortable, but we're kind of like chilling here. Lit. 3B is like the actual like super important stuff now. Okay, cool. So this is where it like starts to get kind of confusing, but it's not. It's really not that bad. So yeah, there's like a shitload of time. It's like it's literally a terrible doc. Because they put like, yeah, they put so much shit in here that's wrong. Okay, that's actually right, Hollow. So that part is right, but some of the other stuff in here is, unless they corrected it, which it looks like part of it they did, but there's a lot in here that, or at least that was wrong. So let's look at this problem real quick. It says build a 2K by 4-bit register file using any number of 1K by 4-bit register files. Okay, so when we see this number, the 2K, that's specifying how many registers are going to be inside of the register file. Okay, cool. Thank you. So yeah, so the 2K or whatever is before the multiplication sign is pretty much how many register files there are going to be, right? So in this case, there's 1,000 or 1,024 if you want to be technical register files in here. each one is 4 bits. So the 4 after the multiplication sign is saying how many bits each register file has inside. And so that's just saying that like any data that's given to the register file should only be 4 bits, and the outputted data will only be 4 bits. It's just like keeping that trend along. It's just another way to, honestly, another way to get credit. But so like your D in is a 4-bit and D out 4-bit. And so your address is a 10-bit, right? And we know that because you have to be able to select from 1024. And so if you were to put like a mux or a decoder, up to it, then you would have 1024 options, which is 2 to the 10. So 2 to the 10th is like 1024, right? And so in the case that it wants us to build a 2K or a 2048 or register file with 2048 registers inside of it, then we just have to add one more bit, right? Because in that case, if it's 2 to the 11th, that's 2 to the 11th is equal to 2048. So in this drawing, right, we look and we see, okay, now we have 2 individual register files and an address that is 11 bits now. But when we look at it, these 1K by 4 can only take 10-bit addresses. So it's like, okay, well, how can we do that? So if you look at it, right, let's just say we'll do it for only a couple bits, but let's just say we have these. And then, yeah, keep going. I think that's all of them. No, wait, there's one more. Cool. Okay. So before we get into like the other section where the significant bit is, right? Like these are all the ones you can have. And then when we change, so the most significant bit is now 1, we have all of these, right? Yeah, we'll get there. Give me 1 second. Okay, so if a 2, I can't do that. Looking at what right on. Let me see. That was sticking up. Cool. Okay, so if 2 to the 10th, right, which is saying that like 10 is how many bits our memory address is here, right? So if 2 to the 10th is equal to 10,024, or our 1K register, right? And we want a 2K, which is equal to 2048. That's just doubling, right, what we had before. And so that's just multiplying it again by 2. So it just makes it 2 to the 11th. So 2 to the 11th is equal to 2048, right? And so we're saying that we want it to have 2048 registers inside of it. And so in order to do that, right, we're going to take a look over here. And so this is like a really like shortened down, like obviously this doesn't have 10 bits, but it only has 4. So, but like if we look at each of these 3 bits, right, they're all equivalent to what is here on this one as well. The only difference is the most significant bit being 1. Does everyone understand that? Everyone cool with that? These 3 bits are the same for all of them other than that first bit. Okay, cool. So let's bring all that shit up. Okay, so if we look over here, then in order to make it double, right, all we have to do is add, yeah, this is the thing she did last lecture, Chris. We just have to add one more bit, right? Because now we're looking at a bit address, which is 10 to 0, because this is 11 bits. And so what we can do, because these 1K register files only take 10 bits instead of 11, we can just take that most significant bit which differentiates between this group and this group, right? We take that most significant bit because the only difference is that first most significant bit. And then we just take it and we use it to choose which register file we're going into. And then I'll explain like more of like this inverse and the and everything like that. But does everyone understand? Like we take that one most significant bit in order to choose which register file. Okay, cool. Cool. So from there, the 10 bits go into the register file to, okay, yeah, what's that? Okay. This 1K register file, right, only has 10 bits going into it. Our 2K register file has 11 bits going into it. Okay. The only thing different between if this is like, if this highlighted section here is this register file and this highlighted section here is this register file, the only difference between these two is that most significant bit, right? So if we take out that most significant bit, we can use that to select between one of these two register files. Does that make sense? Yeah, the most significant bit is A10. Yeah, exactly. We're alternating between the two individual ones. We're going to get to the read and write in a second. So it's A10 and not A11. The same reason that when you look at a 4-bit, it's 3 to 0, right? So like in this 4-bit, it's 3 to 0 instead of 4 to 0. Because we have 11 bits and we have 10 to 0. Because like, just think like computer science, right? Okay, cool. Just want to make sure. So we're alternating between those two 1K registers here and here with that most significant bit. Cool. So as we like continue to go into it, we take out that most significant bit. All the other bits for the address go into the register file to choose which register file inside, right? And then that most significant bit, if it is 0, we invert it, right? Because we want to look at this first register file. So we invert it, so it's 1, and then we AND it with our read and write signal, right? And so if both are 1, then this is actually 1 and high. It's considered like of high status, right? So it's writing in that case. And in the case that the most significant bit is 1, meaning we want to look at this lower 1, then it ands here, and this is true. And if we invert it, then it isn't true here, and so it's just showing like the difference between these two. The D in is the data in, right? But we don't really care about that much. It's just going into both register files. And the read and write signal, excuse me, the read and write signal is pretty much which allows you to change what's inside of the register. So A is the address, like the address. Let's say that you have 1024 registers inside of this register file. The A just chooses which one of those like register files. Each one has its own address. Read and write is like enable. That's what I consider it pretty much. If it is 0, you can still read from either one of these, right? But you just won't change anything inside of it. So that's why we also have to take this most significant bit and take it over to this mux at the end, because we have to still choose which file we're reading from. Yeah. So the memory address, right, goes to both this register file, the 10-bit memory address, excluding the most significant bit, goes to both register files. Okay, it chooses whatever register from inside of there, from inside this one that match up with, like, again, simplified, but these bits. And then from there, the most significant bit is given to the mux at the end to choose, like, did I want from this group or did I want from this group? And then that's what's actually outputted. The read write signal is just there for the data input if we want it to be rewritten. So if it's on, if it's 1, then we actually write into that register and it changes before it's outputted. If it's 0, then it's not changed, and whatever was there before is what's output. Does that make sense? Okay, so the most significant bit is used to either read or write, change this signal, the read or write signal, if we have to write to it or read from it. And then it's used to select which one of the 2 register files to actually use the address, this address. It doesn't expect 11-bit answer. So the 11-bit, and then I'll explain the next thing after, but the 11-bit is just the address to it. When we specify 2K or 2048, the register file, you can make that with 2 1024 register files, right? And it's not actually specifying that the outputted data needs to be 11-bit, right? Because in this case, we just want the outputted data to be a 4-bit, as specified here. So it's just specifying which register to get the data from. It doesn't want an 11-bit answer; it wants a 4-bit answer, as like specified right here. Oh, we'll get that. If you had an A register, it would be, if you had a register file, if you wanted to have an 8K register file, it would be 8K by 4. Or it would be, if you wanted to make an 8K by 4 register file using only 1K by 4 register files, then there would be 8K 1 by 4 register files, right? No, there wouldn't. Wait, hold on. Okay, hold on. Let me do the math. What is it? 40, 96, and then 2 to the 13th is equal to 8. Oh God. 92. Is that right? I think it's right. Which means that you would end up only having this says 1,000. This is 20. That. Actually, no, you're right. You're right. You would have. Sorry, you would have 8 1K by 4 register files. Yeah. Yeah. I'm just thinking of it crazy. If you keep double, right? And then you could like simplify it into having like 3 2K by 4 or 2 of the other ones. But yeah. Why are there 2 ands connected to each other? So the most significant bit goes to both this one and this one, and then the read and write signal goes to this one and this one as well. They're not like technically connected to each other. Yeah, it's from the read write. The CS is the chip selector. I'll explain that in a second when we get down to that question. Yeah, exactly. That's why I was getting confused. So the most significant bit, right? Again, well, let's correlate this register file to these bits and this register file to these bits. Okay. And so the difference again between these two is the most significant bit, which is one here. So let's say that this is the 0 for the most significant bit, and this is the 1 for the most significant bit. So when we take out that most significant bit and we look over here, when it's 1, we're reading from this register file, and when it's 0, we're reading from this register file. And so when we take this inverter, we want to make this AND gate true for the read and write when it's 0, because this is the 0 one, so we just invert it to 1. And then this one, if it's 0, we obviously don't want it to, but if it's 1, it's already going to. So I mean, if you wanted to start out with this, when you start out, you should look at, say, okay, I have K by 4 bit, right? And then you say, okay, I know that means that we're going to have an 11-bit address because we have to choose from so many registers. So you start off here, and then you say, okay, I know I can only use these 1K by 4-bit registers, okay? Which means that I need to take 1 bit out of them. And so like, okay, well, great. What do I have to do now? So I take that most significant bit, and then now I have the proper address for each of these registers. So you say, okay, now I can put the address into the registers because they both take a 10-bit address, and now I have a 10-bit address after getting rid of the most significant bit. If I disable, what happens? Okay, give me a second. Hold on. So then from there, right, we get to, you have your address going into both register files. You say, okay, the most significant bit, when the read write signal is 1, we need to rewrite to this register. Well, this most significant bit when talking to this register file is going to be 0. So we have to invert it to 1 to make this true, which gives this read write signal 1. If the read write signal is 1, whatever data down here that goes into the input, that data is going to be that data is going to be written into whatever register is selected. If A10 is 1, it picks the bottom one, right? Because if A10 comes down here and it is 1, and then it's going to pick the bottom register file. Right? Because if you just follow the path, it goes here into the mux, and then it selects 1 instead of 0. And if it's 1, then it goes down to this section. Darlene, does the first register store the first half of the possible address in the second? Yeah, pretty much. Right? The first register, and it's just because that most significant bit can differentiate between the two. So we need the inverter for the first register because if like the most significant bit is 0, right? If it's 0, we want to talk to the first register. Okay, and if it's 0 here, we want it to be true for this case. In the case, like if the read write, if it's supposed to write, does that make sense? You need to change it from 0 to 1 in order for this part to be true. Okay, and then MVS and the most significant bit in the read register. Yeah, exactly. Significant byte, or yeah, the most significant bit determines which register we're going to. The read write only determines whether or not we're going to read. Does that make sense? So think of the read write. Let's think of it if it was just like this register. If it's 1, then we're writing to this register. If it's 0, we're just reading from this register. But we're still going to get an output here, whether or not we read or we write. It doesn't matter. We're still going to get an output. So in this case, we just want to write. So we want this to be 1 if we do want to write. So if the read write signal is 1 and the address is 1 together, and when you AND them, it makes this 1 as well. But we're actually like selecting which register file to go through with the most significant bit, choosing from either this half of our addresses or this half of our addresses. Does that make sense? So the mux just chooses, right? Because the mux is the bit. So the most significant bit chooses either 0 or 1, right? If it's 1, it chooses from this half of the registers. And if it's 0, it chooses from this half of the registers. Yeah, we don't care what the register really does. We don't care what the data input is. We don't care what the address is for this register. We just care choosing between one of these two registers. We talked about choosing from registers inside a register file in quiz 2. So we don't need to get quizzed on that anymore. It's like now we're trying to make multiple register files together, which is like part of what a CPU is, I guess. And so like it's just bringing it up. So taking smaller parts and then we abstract those parts into seeing something else. So like next week for the next quiz and everything, like this part might be abstracted. The most significant bit chooses this register file or this register file. And the address, everything excluding the most significant bit, chooses which register inside of the register file. I don't know, that was kind of confusing. So this is a register file. Inside of it, there are registers. Those registers individually can take data and blah, blah, blah. It's stuff we've seen in previous quizzes. Only A10, the most significant bit, is going to the mux. Not all of the bits. So like if I was to draw out the lines, right? This line goes into here. This one also comes down and goes down like that. It's just like, yeah, at the top left, it's split. So it splits and it ends up only giving 10 bits to this section. And it takes that 11th bit and it brings it down here. It is definitely poorly drawn. It's just confusing to see. But yeah, so this is a register file. Inside of it, there are registers. The registers are defined, are like selected based on this address, but you have to select between this register file or this register file based on the most significant bit. Yeah. They have to be connected because A10, like it comes out of A10 to 0. That's what I think. I don't think she's going to talk about any other example for the other stuff. I think even more so, it's only going to be specified to ROM because I don't think we had a RAM question, did we? Oh, we did have a RAM question. Okay, so yeah, so ROM and RAM. That's what I think. I don't think it's going to be any of like the SRAM or DRAM, whatever other stuff we talked about in class. I highly doubt that. Yeah, so those are like the only other questions and stuff. The quiz topic was yeah, SRAM, DRAM, ROM. I think SRAM and DRAM are going to be considered just under the RAM section because I don't think she wants us drawing out all the logic gates. I mean, she asked in class about these sort of notations, right? And everyone was like really, really confused with these. So I don't think she's gonna have us draw this sort of stuff out. I think she'll have us draw the other stuff. Yeah, I think she'll only have us draw maybe like register files out like this sort of stuff. I don't think so. I just know that it's RAM, random access memory that you can read or write to. And so that would be an example for this one, DRAM or SRAM. And then just know that ROM is only like read-only memory. And so that's why we only have the chip select. Yeah. Why is mine so blue? I have no idea. Someone said they re-uploaded it recently. Maybe that's why. Okay. Are we kind of good on this problem? We get that we make it bigger by adding one bit because that's multiplying by 2. Are we chilling on that? Cool. 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 So let's look at the next one. This one says build a 512 by 8 using any number of 128 by 8 bits. So again, this is just smaller stuff, right? So 2 to the 7th is 128, right? Because 0, wait, not, yeah, or 2, 4, 6, or not 2, 4, 6, hold on, let me do math. 2, 4, 8, 16, 32, 64, 128, right? So 7 is 128. And so 512 is 2 more, right? 512 is, it goes 128, 256, 512, right? So that means we have to have a memory address that's 9 bit, right? Does everyone kind of understand? We're chilling there. So that means that we take those 2 most significant bits and those go and become our selector for which random access memory we're going to read. Does that make sense? And in this case, we have to use a decoder because it's not as simple as just like a 0 or a 1, but it can be multiple. It can be 0, 0, 0, 1, 1, 0, or 1, 1. And so we have to use a decoder because it's 2 bits to choose and select which one of these we're going to actually read from. Does that make sense? Cool. CS is chip selector. And think of it again as like an enable. It's pretty much the same thing. It's like a load sort of thing. When it's, yeah, that's pretty much, that's how I'm going to say it. That's what I'm going to say it is. It's just like the enable. And so again, we have to use the AND gate because the CS is always going to, let's just say the CS is always, but we don't know which individual one to go to. So we have to use the decoder to choose to AND with something to actually make them 1. Because everything, all these, let's say it was 0, we're looking at this register or this ROM. Then if it's 0, this one will be 1, but all these other chip selectors will be 0. And so in that case, we come over, and once again, we take those 2 most significant bits, and those go into a mux to choose from. Okay, so the reason why there's 4 ROM, the reason there's 4 ROM is because you have 512, right? So 128 plus 128 plus 128 plus 128 is 512. Yeah. And we know that there's going to be 4 because we can say if we want 512, right, that means that it's 2 to the 9 compared to 128 being 2 to the 7th, which means there are 2-bit difference. And if we have 2 bits and we put those 2 bits into a decoder, that means that we're going to have 4 options from those 2 bits. And so you can just like check multiple ways, saying like 128 times 4 is 512. If we have 2 extra bits, that means we're also going to have 4 other options, which means we have to have 4 128s. Yeah, so it's all about splitting your input and then taking that input that you split and using it to select from I mean, it's the same thing. Oh yeah, 3A versus 3B. Yeah, the 3B was like a lot more homework wise. Okay, so with the 2 most significant bits, we take those and use those to select. So if I was to change, yeah, it gets a little bit more confusing. Yeah, exactly. So instead of just having 0 or 1, we have 0, 0, 0, 1, 0, 1, 1 as our 4 possible options, right? Because those 2 most significant bits will either be 0 or 1 individual, but that means that we have 2 to the 2 options, which is 4. And so because we have those 4 options, we also have to have 4 different ROM. And because we want 512, we want 4 anyway, because we want to have 4, or 128 times 4 is 512. So the problem says build a 512 by 8-bit ROM using any number of 128 by 8-bit ROM, right? And it even tells us here it should have a 9-bit wide, right? And so from there, we can just build up to a 512 by 8-bit. Luckily, because it's 8-bit, we don't have to expand horizontally. But when we expand vertically, we use that as just expanding the first number. So to go from 128 to 512, we need to have 4 128s. Does that make sense? And just think of like, so think of if it was like if I have a, what do you mean they updated the homework? Is there more homework now? They add more problems? Oh, oh, okay, cool. Sorry. Okay, so if you had a let's say I have a 16 gigabytes of RAM, right? If I have 16 gigabytes of RAM, I can have it as one 16 gigabyte stick, or I can have it as 2 8 or 4 gigabyte sticks, right? So if I can separate it into multiple kinds, but if I only have that individual like 4 gigabyte stick of out of like all my 16 gigabytes, if I only have one 4 gigabyte stick, then that's only allows me up to 4 gigabytes of options. But if I have 4 gigabyte sticks, then I have 16 gigabytes of options. Does that make sense? So it's just like it's the same sort of concept, but it's kind of, yeah, pretty much. Like you're just allowing for space. So without having multiple, then you're not gonna have um if you don't have more, then you aren't gonna have the space. So it's just allowing you to have the space. Yeah, yeah, equivalently. It's only gonna use instead of like having to go into your hard drive or something like that to store stuff. If you wanted to be like kind of technical. if you just remember that, if you just remember however many bits an address needs to be, that's the most important part. So like in this case, you have 128 memory, let's just call them memory slots inside of this ROM, right? And you pretty much say like two number of bits is equal to 128. And you're like, okay, well, that's 7, right? So 2 to the 7th or 7 bits is equal to 128 options. And so we need 128 options to choose from one of these 128 memory slots inside of this ROM. And that means we have a 7-bit memory. If we need to increase it, right? If we need to increase it to a larger size, say 512, well, 512 needs a 9-bit wide address input, right? And if we need that, then that means that originally we take those 9 address bits, right? And then we take 2 of them because we are only allowed to put 7-bit memory addresses into each individual 128 ROM. And from there, we need 4 bits. 2 bits gives you 4 options: 0, 0, 0, 1, 1, 0, or 1, 1. From there, it makes a selection from any of your 4 options that are legal. It needs to be legal, right? So this can only take 7 bits. You're given 9 bits, which means you have to get rid of 2. So you get rid of 2 by making a selection, and you make a selection by making more options. Does that make sense? RAM is random access memory. You can read or write to it. ROM you can only read from. It's read only memory. Yeah, so 2 bits is missing. And so we need to do something with those 2 bits. So what we do is we use the 2 bits to make a decision. And so those 2 bits we take and we use them as a selector. And so we throw them into a decoder, because what a decoder does is it selects. It takes an input and it selects out of that. And so you get 0, 0, 0, 1, 1, 0. And from there, you're able to have like your option of 4 inputs with still having a 7-bit memory address, which makes it legal for your 128 RAM or ROM, sorry. Fuck. Okay, we're gonna go on to the next one real quick. Oh, fuck. Okay, what's up? Yeah, I have water, thank you. Oh, Paprika has a good computer. It's gonna take a while to process and upload it, or good internet at least. And take a while to upload and everything. 3 hours is a lot. Yeah, that's a decoder though. So it goes to both. Yeah, sorry. It goes to both the decoder and the to the mux to choose. It goes to the decoder to It goes to the decoder to do the chip selector part, and then it goes to the mux to actually choose which one the output is going to come from.
Hello.
Hello. Hello. All right, we're gonna go to the next question real quick. Cool. So this last question, shit. Oh, there's 2 more questions. Let's do. Okay, for real quick, we're just gonna like briefly look at this one because this talks about RAM, just so we have an idea of what to do with RAM. With RAM, because it isn't just read-only memory, right? It's random access memory. It's volatile. You can read to it. You can write to it, or read from it. You can write to it. And so in this case with RAM, you also still need to have the read-write signal, but it's different than the chip selector, right? So just think of the chip selector as like a load, and the read-write is actually if you're going to read or write to that RAM. So the concept of building it is the same. You need to take that extra bit and choose from there, blah, blah, blah. All the other stuff that we talked about earlier with this problem. Yeah, that I like this. Think of the chip selector, I guess, is like a load. So it loads like this one, and then the reader write specifically says, hey, am I going to read? Am I going to write? If it's enabled, then you're actually writing to it. But so in this case, you can see like something that's like different is that the read write signal, right? It doesn't have to be anded or done anything. Anything else is done to it. It's just like it goes directly there if it's going to be 0 or 1, and that's because we have our chip selector, right? So in the case of this one, we had to and it because it's only read and write for a register file. But for down here, we don't need to because our chip selector already chooses. And so the reader write is always either going to be 0. Granted, it still needs to go down to the mux, and that's where we can see it here, to choose which one of these two, but it doesn't need to have the and with the read write. Are we kind of like, we see that? We're good?
Which problem is this?
What's up?
What problem is this?
This is 4 on homework, or 3B.
Which number?
Number 4.
Okay.
Cool. Are we solid on that? Illustrated better. Hopefully, hold on. Yeah, honestly, the lines like this section, fuck fest. Yeah, and done a lot better if they explained it for us like here, and if she actually like talked about it. Like these solutions got posted before she talked about it, and like the TA was like, oh yeah, you just take off this most significant bit and you can just like specify it by using, like, you can index it, right? So in Python, you can index out of a list by giving it a number. And so like, that's the same concept here. Like you have a, let's just say a list of 10 bits and then you index out of them. That might be like a good way to understand it, except it's like backwards. You don't index from like 0 to 10 units, 0 or whatever. So it's a little bit weirder, but that might be like a good comparison. Anyway, so RAM isn't that bad, but I kind of want to like go over this question fast because it's the same concept, just a read and write signal. It's different. Yeah, and we'll go over the homework questions, any of the like the study, like the actual stuff, but the notes and stuff. But as your question, I'm gonna like kind of start ish on the next one. I already like read it real quick. So for problem 3 now on this homework, okay, this one is just again the same like concept of building, except now it wants you to build a 2K by 16 bit. Yeah, that's the case. It's only the read write is different, and that's because it's RAM instead of ROM. So all the other questions have been ROM, which are only read, like you can only read from them, and RAM is either one. So you have to have that read write and going into it. Okay, so this question, it says build a 2K by 16-bit ROM. Okay, ROM, that means we're only going to have a chip selector. We don't need to have read write. So we look down here and we look at our answer. The thing is, we only have these 1K bytes, right? So in order to increase this 8 to 16 as it wants, you have to duplicate it, right? Because it wants 16 bits instead of 8. And it wants 2K instead of 1K. So the 2K, it means that you're going to increase the address by 1. Okay. And the 8 to 16 means you also need to double how many are in horizontal order. And so I'm going to zoom in real quick and like kind of see what they did here, which again, like this is the whole concept of splitting and putting together. We didn't really understand because they didn't explain it to us that well. But so you take this ROM and it does everything it needs to do. It gives its output and then it connects it with the output of the second register ROM, in horizontal succession, making a 16-bit, right? What Bailey's saying is that for the first section, right, from going from a 2K to a 1K is how many rows you're going to have, because you need to be selecting from the 2048 options, which individually has 1024 here, 1024 here. And then in order to get from 8 bits to 16, you need to coincide, or you need to put together two 8-bit registers. And so that's what you do here. You take the 8-bit register that you get from here, and you take the 8-bit register you get from here, and then you put into here. The 1K is 1000, but it's just simplified. It's 1024 technically, yeah. It's just the 1K is simplified because they're too lazy to put it on there and it saves space. Yeah, so in this case, the only difference is you need 2 in order here. And okay, I'll explain it again in a second. But so the difference is 2 in order here, right? Because you want 16 bits and they only come in 8 bits. So you need to put 2 together to make 16 bits. What Bailey's saying is that we're going, let me zoom out real quick. So like a little too close. Yeah, they're literally just concatenating. They're not doing anything else. They literally just put them together. And I mean, I'm okay with that. Like if it's that easy, then fuck it. But so Bailey is saying that if you go from a 2K, right, 2K, or if you go from 1K to 2K, okay, that means you doubled it, which means you also have to double the number of options. So let's say this is 1 option and this is 2 options. And you went from 1 option and now you want 2 options, which means you had to double it. So in this case, it's the rows. And then if you're talking about bits though, instead of like how many options, if you double the bits, you have to be able to double this number. And so you just take the second number and then you combine it with the first number. So the first number in this section here is how many register files, and the second number is how many bits. If you start off with only 1024 register files where each one is 8 bits, and you want 2048 register files where each one is 16 bits, we already built a 2000 by 8-bit ROM, right? So now we just think, okay, well, what can we do to make it 16 bits? Well, we can just add another one at the end and combine them together as we did here. So we took the register from here and the register from here and put them together as our output. Does everyone kind of see how that works? Like, kind of solid on that? Yeah. Yeah, each mux, or the mux takes in two individual 1K by 16 register files. and chooses which one it wants to actually output from there. I mean, yeah, it does, but you just have to remember that the register file, because you have the address automatically chooses only one register. So it's not technically 1K, it's not like technically 1024 registers, but it's only one register out of like the 1024 register options that actually goes into the mux. So the mux will only have the option of choosing from a 16-bit register out of this hole, and then a 16-bit register out of this one. And then one of those two 16-bit registers will get outputted at the end here. Does that make sense? Okay, I just wanted to make sure. We're gonna do I'm gonna go over it really, really quick in like 6 minutes, and then we're gonna go over all the problems again tomorrow and just make sure everybody kind of chilling. Shit, almost fell. Number 2 is way too long. Is it? Maybe not. Oh yeah, no, we're definitely not gonna do number 2 on the assembly one. But yeah. Let's just talk about this one real quick. Yeah, no problem. Okay. So it says we want to update the value of the register T0 to 255. So fill in the blanks. Okay, so if we immediately address something, right? I believe the TA said like load LI, but he didn't give us that as an answer, obviously. So for immediate addressing, right, we say we add into T0 plus 255, which just automatically gives us our answer. Does everyone get that first section, this part? I feel that. Okay, cool. Yeah, it's very similar to the lab. He said we could, but just to be safe, I'm gonna follow what he had here. So I'm gonna use Addy types of stuff. Yeah, just to be safe. I'm like immediate addressing technically is load immediate, but I mean it literally says load immediate, but I'm just gonna stick with the Addy. Okay, register addressing, it's not immediate, so you're not gonna use like the Addy, but instead what we can do is we can add T0, and just remember that each time, each one of these questions, like it resets, so T0 is back to 0. So we add T0 to, T0 is equal to T0 plus T4 because T4 has 255 inside of it. We're good there? Cool. Cool. And then what's the difference between A and B? A uses the number because we're immediately addressing instead of looking at a second register. We're just giving it like 0. Yeah, we want T0 to have the registered value 0 with 255 after. Yeah, so when you register address, when you're not doing immediate addressing, so immediate addressing is you're actually giving it a binary number. Not for the second one. For the second one, because it says use a register addressing, you have to grab the T out of like what's given to us. But it's given to us right here, so it's not that bad. Okay, for part C, it says base addressing, right? So remember when you see parentheses, it means that what's inside is an address, and we're looking at the value in the address. So it says, okay, we're still trying to make T0 into 55. And so we load byte. We load byte because if we load word, if we load word, that's going to take up 4 addresses in the memory. So instead we use load byte, and we see that T3 right? T3 has a value of 6, and the memory, the value at address 6, when we use parentheses, it says like inside is an address, is FF. So we can use that. Does that make sense? You do have to use the parentheses because this is addressing. This is base addressing. And so we're grabbing the value from the memory address, and we want FF. So you can, like, the best way to work this question is to look backwards, right? So we want T0 to equal 255. So we look in the memory and we say, okay, well, 255 comes from memory address 6, okay, and then register T3 has a value of 6. So we can put T3 in parentheses, and that's going to give us the value at the memory address 6. The LB, the load byte, puts the value at memory address at a memory address 6, which is 255, into T0. I don't know what you're talking about. We were all on here. There was a lot of talking about the lab on this Discord, like a lot of talking, like for the past, like, literally, no, not you, Arcari, but like about lab 2. Like, we've been talking for literally like the past, like, week, like, how that shit. It's been a bitch, but yeah, for at least the next lab 2, because I know what the next lab's gonna be. So yeah, it's gonna we'll definitely be on here. So yeah, so we'll be talking, I'm sure, a lot of, again, for lab 3, but lab 3 is the last one, so that's cool. Okay, sorry. Last one. So the difference between base addressing and base addressing is that when you offset something, you have to put some sort of immediate number to the left of the parentheses, which increases or decreases if it's a negative number. Whatever the value is here, whatever the memory address is here, it increases or decreases based on what is given to check the value. So in T2 is the value 4, right? And we still want the FF. So the value for the memory address here, but if we increase 4 by 2, which is what this does right here, then that gives us 6 again, which means that we're loading FF into plus 2 is it wouldn't be address. Yeah, it would be whatever the value is at address 2. Obviously, we can't see that here, but yes, yeah, they do take negatives for offset. Yeah, it makes 4. It makes the memory address 4 into 6 when you do this. If the hex numbers for our values addressed were 8 digits, we use those words. Yes, you would use if they were 8, you would use load word. They're not going to give us a load word because they haven't done it for any of the other, like, the previous quarters for quizzes and stuff like that. They're not going to do it from now. Like, yeah. So for this one, T2, right? Okay, so again, I'm just going to start from the beginning. Base plus offset addressing. Again, we need 20 to be 255. I'll just do it again. Screw it. And so we look at, again, 255. Okay, but we actually, like, is address 6, but we need to actually get it from, like, changing it around. So what we can do instead is we can do take the 4, which is T2, and then we can increase 2 to it, and that gives us 255. To T3 is going to be 4. Yeah, exactly. Okay, and then if you theoretically could do, like, for example, like on the quiz, they might not give us a register with a value that actually works. So let's say the memory address was 6 and none of this wasn't 4. What we can do is you can just say load byte. I'll write it down so, like, you guys can see it in written now. But you could say load byte B0 T0, and then you would say 6. You could do that, right? Because this says, okay, from the value at memory address 0 plus 6, so that's this one, put this value into T0. So that's like your other option. So in the case that like the quiz doesn't have a feature that has a way that works, you can just actually like do it yourself. So theoretically, like if the memory address was say like 5042, you could literally put like 5042, like theoretically. Yeah, exactly. And you have also have to remember that the base plus setting or addressing, you cannot use like the 06 and then offset by 0. You always have to offset by an actual value that's not 0, because this base addressing is theoretically adding by 0. So you actually need to give it a value. So if you couldn't use this. And then I think it was someone Pat, or no, it was someone was asking earlier. Where is it? Yeah, Paprika, you were asking earlier if they would, for the first one, if they would accept load immediate, like LIT00XFF. No, kind of maybe. It should theoretically be accepted, but the TA gave us this answer, and someone asked during discussion too, like, could we just use load immediate? And he said yes, but maybe. And so he just said use the add immediate, and you'll get 100% for sure. So just use this one. It's not like that confusing, I guess. Yeah. Honestly, the only reason I go is because I just go get Chipotle before and then chill. You can read a book or some shit. Like it's getting Chipotle is motivation to go to discussion. No, it's a really good book though. Li in word. No, it's really good. It talks about called 21 Lessons for the 21st Century. Super good book. It talks about like how neural networks and AI are going to play into the future, or like someone's opinion on how it's going to work into the future. Super, super interesting. This is going to be the same type of assembly question on the quiz. Yeah, more likely than not, assembly question. But the second one we're going to talk about tomorrow. So yeah, we'll talk about that tomorrow because that's like a longer question. But I have the code written. I think I posted it somewhere. I'll find it. I don't think so. I really don't think that they could dig you question. I mean, granted, it's not that long. I think it's like it's not really not like that long of a question, but yeah, I don't think he would do that. Yeah, I mean, realistically, like if you previous quizzes for different classes have shown that this quiz has these sorts of problems. So that's what I would compare. I don't even think it's going to be similar to what it was. I think it's going to be maybe like multiple types of these questions, or maybe filling in these answers. So like it'll give us an some sort of code like this, and then actually writing in the input. So yeah, kind of like actually the last quiz then. But yeah, previous quizzes have not shown this sort of question being on this quiz. That's going to be great. So that is basically number one. What do you mean? Paprika recorded this. Like the different types of ways to do the same thing. Basically, number one. Yeah, exactly. They're all doing the same thing. It's just different ways to do it, based on what's given to us. Because this isn't necessarily always the case. So yeah. Yeah, it's pretty much the same thing. And then Paprika, when you actually like post it, can you just add admin and then one of us will pin it. Thank you. Okay, really quick because that's kind of important. Well, like 5 minutes, and then I gotta do stuff because I have to work tonight in a couple hours. Let me see.
Oh shit! Hold on. Fucking headphones died. I know, me too. Fuck. No problem. Okay, can you guys hear me? Just one person put yes or.
Yeah, you can.
All right, cool.
Good job.
It's
Dude.
like
You're better
yeah,
than me.
Yeah, you're good, bud.
lit. Thank you. All right. Okay, let's talk about adder subtractor real quick. Okay, so an adder can also be used as a subtractor if because if you do this, so like a plus the inverse of b plus 1 is equal to a minus b. All right. And so if we find a way to make this happen, we can use an adder to do a subtracting problem. Also, definitely not going into academia, screw that shit. Trying to make money, not teach people. But anyway, so okay, real quick. So this is an example of an adder slash subtractor, right? So if E is equivalent to our C in, which is our carry in, right? And our carry in is if 0 is an addition problem, and if it's 1, it's a subtraction problem. Then what we can do is we can put that E into every one of these muxes, as well as the full adder, and we're able to do either one of these problems. So in the case that in the case that it's a 1 put in here, we're doing a subtracting problem. That 1 also goes to this mux. That mux reads the inverse of b, and then it adds a plus the inverse of b, and then it plus the 1, and it goes and it carries in to here, and then it does the same thing here, and it takes that and it outputs the value, and then if there's a carryover or overflow, then that's what the carry out is, and that goes into the carry in for the next one. And then again, the value comes out here, and then if overflow, that goes out into the next one as the carry over input. Okay. And so in the end, you're gonna, if you're doing a subtraction, you're gonna have a 1. That's why, like when we were talking earlier about I think I erased it, but like those problems where it was like if you're doing 1 on 1 times, or I'm sorry, subtracted from this value turns into plus 1, which makes it this, right? And then you add these two variables together. This is what, like, something that you put inside of an ALU, right? And so, for example, if you want to look at the ALU, where is it? Register file is a register file. Let me find it. It's further down here. So for example, here, ALU, like you have that mux here, which goes into the adder. And so, but once again, it's like this is what we talked about earlier. Once Paprika posted, you can kind of go back and look. But the difference between addition and subtraction is the most significant bit. We look at that most significant bit, and it distinguishes between either taking the inverse or just taking the normal, and then you add those two together. And if it is you're taking the inverse and you're doing a subtracting, that also goes in here as the carry in, which gives you the correct answer. And the carry out is always going to be discarded unless specified otherwise. At the end, the carry out at the end of your ripple chain is always going to be discarded because we know that we did a subtraction problem. That's cool. We can go over the adders and ALU stuff tomorrow as well. Like as a brief thing since it won't be recorded, but it's cool either way. So yeah, does that kind of make sense for people? So the carry out is just getting rid of because the carry out is just saying that we have a 1 in the front and we already know that it's subtraction. So we don't want that 1 in the front. We just want the value that was actually subtracted. And that's what's given here. We solid? Shit. Any questions or anything like that? Sorry. Yeah. Okay. Real quick, I'll post in the off topic again, but tomorrow's probably going to be like 6 because I'm meeting with someone and we're going to talk about 45C and work on that tomorrow. So probably like 6-ish tomorrow, but I'll post that in the off topic again. Cool. All right. No. It's chilling. It helps me study too. Thank you though. But yeah, y'all, Paprika, when you're done and it uploads, I have no idea how long it's gonna take, but yeah, good luck. But yeah, after just add an admin or something like that, and then or I don't know, can people pin? Can anyone pin stuff or?